Welcome to Fluid Mechanics, where we make complex concepts flow smoothly. I am Aryan, your guide to make things fluid.
And I am Ajit Gupta, the curious mind who is always asking, but why? Today we are lacking something called the cell momentum balance.
It sounds like intense, right? But we will go in step by step to understand every complex things to make it into similar way.
Okay, first thing first, what is cell momentum balance and why cell? Are we talking about something like turtle or eggs?
No, it's not like that. It is a tiny slice, like an onion layer from a flowing fluid, and the cell. The cell is basically the onion layer from a flowing fluid. And the balance is just accounting for all the forces acting on it. That is the pressure force, shear stress, and the gravity force due to gravity.
So it's like doing a force balance, but for a fluid. Why not just we use the Newton's law? Why we need this?
Great question. Newton's law are just the foundation. But for fluids, since fluids are very much squishy and continuous, the cell momentum balance simplifies the math by focusing on small control volume, turning a complex partial differential equation into a solvable ordinary differential equation.
Alright, but why is this so important? Can't we just let fluid to do their things?
Yeah, it's great question. But the thing is, if we do not know how the fluid varies and why we do not know the properties, how the fluid changes its velocity profile or the shear stress at the interface or at something, we do not we basically try to design reactors. So to design reactors, we try to know the fluid's property. So that's why, like we can say that in real world design, engineers use this to predict pressure drops in pipes or to optimize reactors. It also used to predict the velocity profile or stress profile. Ever wonder why syrup flows slower than water? This balance explains you. And also, it is the foundation for our advanced transport phenomena, or we can say computational fluid mechanics.
Okay, got it. So it's like ABC before writing novel in fluid mechanics.
Yeah, we can say that exactly.
Walk me through it. Where do we start?
So, to start, for cell momentum balance, first we have to select our coordinate system. That is, which coordinate, like it depends on. We have seen in the flow through falling film where we choose the Cartesian coordinate system, and flow through pipes where we use cylindrical coordinate system. There also a flow through a sphere where we use a spherical coordinate system. So there are three types of coordinates. Depending upon our system, we choose our coordinate system. And the second one is we have to choose the velocity in which direction it is flowing. Like it is flowing in for Cartesian coordinate system, it is x, y, or z. For cylindrical, r, theta, or z. Depending upon that, we have to choose the flux momentum. Like there are totally nine components, so which are non-vanishing. We have to identify that. After that, we have to write the all momentum balance equation, and we have to just put the cell momentum balance at steady state.
Wait, but how we do some forces on a squeezy fluid? How?
Think of it like this: if pressure is higher on the left at compared to the right, then fluid gets pushed, but viscous drag fights back, balance the two equation, and that's we got our equation. In that way, we will get the equation.
As I keep hearing about boundary condition, why it is so necessary? Why we need?
So yeah, boundary conditions are very much important with cell momentum balance. Like we have shown, the equation which we got are partial differential equation or ordinary differential equation. So to get the exact velocity profile, we have to do the mathematics, that is integration. And by do to solve that differential equation. On solving through integration, we get the constant of integration. And for the exact expression of velocity profile or our stress profile, we have to evaluate that constant of integration. So to get the value of our constant of integration, we use these boundary conditions. So there are basically four boundary conditions we use in cell momentum balance. That is first, no slip boundary condition. Second one is like shear balance boundary condition, and third one is logical boundary condition. That's
So they are like rules of the game. If there is no rules, there is no boundaries, then we got no solution.
no. It's like, yeah, we can say that in that way, because to get the exact velocity profile, we require that constant of integration. So that's why we are using the body equation.
So let's go for the problem number one. This is water flows through a narrow slit. This is our diagram. Water is flowing down along vertical slit formed by two parallel walls with distance delta apart. One wall is fixed while the other is pulled up with a constant velocity v. So this is our system in which we can see that the left side of the wall is fixed, that is stationary, and the second other side is moving with a velocity v. And through this, there is a thickness called delta through which water is flowing down. So this is our system, and assuming that both walls are very long and wide, this is our first assumption that the length and width of wall is very much as compared to this wall thickness. So this is our 3D view, and this is the front view in which we can see that direction of wall is moving in upward, and from here water is going down. So this is, and this wall is fixed. So what we have to use, we use the Cartesian coordinate system. Using cell balance approach, we have to determine the shear stress profile and also velocity profile. So let's go into the problem. So our first assumption is this is the 1D laminar flow, steady state, and also end effects are neglected. So this is our system where Vz is 0, Vy is 0, where this is Vx basically, this is not Vz. Vx is equal to 0, Vy is equal to 0, why it is 0, like we can see that there is no flow in x and y direction. This is our we can see from the flow, this is only, there is only flow in z direction, there is no flow in x direction and neither in y direction. And also vz is not a function of z, which is due to continued acceleration of liquid down the wall. There is no acceleration in this direction, and also due to liquid is incompressible, therefore there is no function. Vz is not a function of z. Vz is a function of x, and pressure is also a function of x. Pressure is not a function in z direction, like due to the liquid fluid is our water is incompressible. This is our assumption. So these are our assumptions through which we will try to solve this problem and try to develop the flux profile and velocity profile. This is our differential cell, which we can see that there are the three flux that will arise due to flow in z direction. So this is phi zz, phi xz, and phi yz. Since there is no velocity in x and y direction, that is vx is equal to 0, vy is equal to 0, so all the fluxes arises due to the motion in x and y direction are 0. We consider to be 0. So now we will write the z momentum balance. Z momentum balance, that is the flow in only z direction. So only from flow in z direction there is a momentum. So this can be given by phi zz, that is momentum in z direction due to the flow in z direction, due to the motion in z direction, and this is given by P, that is pressure force, rho Vz square, that is convective, and tau Zz. This is our molecular. So it can be given see that my this term will be 0 because Vz is not a function of z. It is stated in our assumptions also. And the second one is phi by z, that is flux in y direction due to the motion in z direction. It is given by rho vy square plus tau by z. This term is 0 because there is no velocity in y direction. The only term left is tau by z, which is also resulted to be 0 because vz is not a function of y and vy is also 0. So the whole term will be 0. There is no effect in phi by z. Now coming back to third, that is phi xz, which is rho vx into vz. Since vx is 0, there is no velocity in x direction, so the whole term will be 0. So remaining term is tau xz, which is minus mu times dou vz upon dou x plus dvy upon dx, where vz is a function of x, so this term will be non-zero, and this term will be 0 because vy is totally 0. So now writing the rate of momentum in this direction, rate of z momentum across z is equal to 0. That is, in this our system, we can see that this is the z direction, and in z direction at input at z is equal to 0, writing the momentum balance in, and at z is equal to L, writing the momentum balance for out. Similarly, we can write for x, that is in at x and out at x is equal to delta x. So this is our momentum balance which we had written like flux into area that is cross sectional area perpendicular to the flow. So in this case we can see that this is our system in z direction, and for this the cross sectional area is this width into this thickness delta x. Similarly, we have written for at z is equal to L and z is equal to 0 also. So write z momentum balance at x is equal to 0. Here same also the multiply flux into multiply by its cross sectional area. Here we can see that this is L into W because in x direction the cross sectional area is this. This is W and this is L. So this is what it is written here. So this is the cross sectional area. Now rate of gravity, that is WL delta x, which is the volume into density into acceleration. This is what basically we have written. So now we will write the cell momentum balance at steady state, which is given by rate of momentum in minus rate of momentum out plus force acting on body equal to 0. That because this is basically accumulation term. In the steady state case, this is 0. So the writing the whole expression, that is phi xz into Lw plus phi zz W. This is the momentum in, total momentum in minus total momentum out plus force due to external agent, that is equal to 0. So on rearranging the term, we get phi xz x plus delta x minus phi xz at x plus W times delta x into phi zz z is equal to L minus this. This is the term. So now we will divide the whole term with this term WL into delta x to get this expression, that is phi xz upon phi xz x plus delta x phi xz x upon delta x plus phi zz z is equal to L minus phi zz z is equal to 0 equal to L by L is equal to rho into Z. So now from the definition of derivative, we try to reduce this expression in this form. Like we know that from the definition of derivative, d upon dx of phi xz is written in this form. So now we will put this value in this, that is d upon dx of phi xz plus phi zz at z is equal to L minus phi zz at z is equal to 0 by L is equal to this. And this here we can see that in phi xz there is only one term left here, that is what, that is minus mu times d upon dx of vz. So this is what here we have reduced this phi xz to d upon dx of tau xz, and phi zz is pressure force plus the convective flux, so it can be written in this form. But we know that vz is not a function of z, so at z is equal to 0, at z is equal to L, vz will be, this whole term will be same, so we will cancel it out. So now we will just make some rearrangement so that we could reduce this expression in this form, that is PL minus rho gl minus p naught. P naught it is given, and rho z into naught. We just introduce this term to make a unit balance. So now this the whole term is reduced to this form. Here this is the reduced form of pressure that is given by PL minus rho GL minus P naught minus rho Z naught upon 0. So d upon dx of tau xz is equal to reduced form of pressure, that is delta P by L. So this is our differential form of shear stress. On integrating, we get the reduced form of tau xz is equal to delta P by L x plus C1. Since we do not have any boundary condition for flux, therefore we directly go into the Newton's law of viscosity. So by just putting the value of tau xz, that is minus mu times dou vz plus dou vx upon dou z. Since we know that vx is equal to 0, this term will be 0 and this term will be non-zero. So by putting the value of this into this expression, we get this form of equation where dou vz upon d upon dx of vz is equal to this. On integrating this expression, we get this expression where we have to find this term. On integrating, we get vz is equal to minus of delta p upon 2 mu l x square plus c1 upon mu x plus c2. We have the now we have two boundary conditions, that is at x is equal to 0, vz is equal to 0. This is no slip boundary condition. And at x is equal to delta, vz is equal to minus v. That is, we know that on the right hand side the ball is moving with a velocity of v. This minus sign indicates that the ball is moving in upward direction and the flow is in near downward direction. So that's why we have taken it as minus v. So using the boundary condition, we will find the constant of integration, this and this C1. So by putting the boundary condition 1, we get C2 is equal to 0, and by putting the boundary condition 2, we get C1 is equal to mu V upon delta minus delta P upon 2L into delta. So by putting the value of C1 and C2 in the above velocity expression, we get the expression as Vz is equal to delta P upon 2 mu L bracket open delta x minus x square minus v into x upon delta. So this is our velocity profile. And to get the flux profile, we have to put the value of C1 in this expression, which on putting we get the expression as delta P by L bracket open x minus delta by 2 plus v into mu upon delta. So this is the flux profile. So now coming back to the problem number 1, it is a case of falling cylinder viscometer. A falling cylinder viscometer consists of a long vertical cylinder of radius r, capped at both ends, that is, it is closed at both the ends, with a solid cylindrical slug of radius kappa r. This is the solid cylindrical radius of slug of having kappa r radius. So the slug is equipped with fins so that its axis is coincident with that of tube. So it has some fins so that its axis should be aligned in the of cylinder. So one can observe that the rate of descent of slug in the cylindrical container with the latter is filled with liquid. So we can see that when this cylinder is filled with liquid or fluid of viscosity something mu, we can see that this slug is descending in downward direction. That is, cylindrical slug descends with a speed of v naught, that is terminal velocity of this. So here we have to find an equation which relates the viscosity of fluid in terms of the terminal velocity of the slug. And we also have to derive the expression for velocity distribution using self-balanced momentum approach. So this is our system, which we can see that this is the cylinder of radius r, and this is slag of radius kappa r, and height or this is h, and this is the radius. So now coming into the problem, we have chooses the first thing to do in self-balanced approach is to choose the coordinate system, and we have chooses the coordinate system as cylindrical coordinate system, where origin is at the bottom, that is origin is at there, and we also coordinates of r, theta and z. This is the z direction, this is r, and this is theta direction. So this is our coordinate system. So few of the assumptions which we consider to solve this problem. This is first, this is 1D laminar flow. and second one is steady state condition prevails, and the third one is end effects are neglected, that is flow is completely developed in this region, there is no external disturbance to this. So this is our assumptions. Also Vr is zero, there is no velocity in r direction. V theta is zero, there is no velocity in theta direction also. And apart from that, Vz is not a function of theta and z. We can see that this is down descends in downward direction, that it has some velocity in z direction, but it is not a function of theta and z, because it is the problem is symmetric about this theta, and this is not a function of z, because it is the fluid is incompressible, so it does not affect it. But the Vz is only function of radius r, which is given there. So as a result of which we can see uh, the velocity has only component in z direction. So it may have three flux component, that is phi zz, phi yz, or phi xz. But since we are in this case comparing to the Cartesian coordinate system, here we have phi zz, phi rz, and phi theta z. But here since phi theta z has no component, because v theta is 0 and vz is not a function of theta, so here we left with only two flux component, that is phi rz, that is the z momentum in positive r direction, and phi zz, the z momentum in positive z direction, will contribute to the momentum balance. So this is our differential cell. Here we have taken this our slag having this is the direction r, theta, and z. Apart from that, this is the height h, and this is the flux entering phi rz at r and phi rz r plus delta r. This is the direction of gravitational force, and from here the phi zz is entering. So now we will write the rate component. Rate of z momentum in cell at z is equal to 0 is given by phi zz into flux into area, that is rate is basically flux into area. So this is phi zz is the flux, and this is the cross sectional area. We can see that this is cross sectional area 2 pi r into delta r. This is the this is 2 pi r, and to its thickness, that is delta r, that is total cross sectional area in z direction. It will remain same at z is equal to 0. This is in and this is out. So now coming back to rate of z momentum in cell at r, that is at this position, the rate of momentum, this is given by phi rz and its cross sectional area, that is 2 pi r into this height h, 2 pi r into h. This is the cross sectional area for this, and rate of z momentum out for at r plus delta r will remain the same, that is 2 pi r, 2 pi r plus this time radius will change, that is this time this is r plus delta r into h. So this is our rate, and component of gravitational force on the cell in z direction is given by minus 2 pi r delta r into h into rho c. This is the volume, and this is our density to acceleration due to gravity. Say we have taken it as negative because z direction is positive in upward direction, and the flow direction of gravitational force is downward. So that's why we have taken it negative. So now writing the cell momentum balance at steady state, which is given by rate of momentum in minus rate of momentum out plus force of gravity is equal to 0. So now putting all the values, that is rate of momentum in, that is rate of momentum in at z is equal to 0 at r, which is given by 2 pi r delta r into phi zz at z is equal to 0 plus 2 pi rh phi rz at r minus rate of momentum out, that is coming out of the surface, is given by minus times 2 pi r delta r phi zz at z is equal to h plus 2 pi r plus delta r h into phi rz r plus delta r. So, and force due to gravity is given by minus 2 pi r into h. On rearranging the terms, that is taking minus 2 pi r common, and phi z at z is equal to h minus this is equal to this phi or 2 pi h r plus delta r phi r z r plus delta r minus r phi rz minus 2 times delta r h is equal to 0. Here we can see that the flux that is going in. Here we have basically on rearranging what we have done. We have taken the minus times this common, so that we actually want to convert this into a form of so that we can get this term delta r terms in the downward, so that we can use the definition of derivative. So that's why we do this arrangement in such a way that delta r should comes in the denominator. So here, as on rearranging and by dividing by minus 2 pi rh, we can see that delta r terms will come into the denominator. And from here, we can use the definition of derivative. That is d upon dr of r times phi rz plus rho zr into r times phi zz at z is equal to h minus phi zz at z is equal to 0 by h is equal to 0. So now we this is our expression. This is our expression which we use to solve our problem for velocity distribution. For that we need is phi rz and phi zz, and we know that phi zz is given by pressure force plus convective flux plus molecular flux. Pressure force is basically a function of z only. Here we have mentioned it. Pressure is a function of z only. To coming back to this, phi rz is given by tau rz plus rho times vz is equal to tau rz. Here vr is equal to 0, since therefore this whole term will be reduced to tau rz, that is only molecular flux. Phi zz has three components also. This is non-zero. Phi tau zz is equal to 0 because vz, velocity in z direction, is not a function of z. So that's why the whole term will be 0. And we have only left with the pressure force and this convective flux. So now putting this value in the above expression of this, here P at z is equal to h plus rho vz square at z is equal to h minus P at z is equal to 0, rho vz at z is equal to 0 upon h plus this is our we came from the definition of derivative, rho times rho zr is equal to 0. We can see that since vz does not depend on z, the rho vz terms will be cancelled, because since vz is not a function of z, so velocity at position z is equal to h and at z is equal to 0 will be same. That's why we cancel this term. So now we taking the common, where p z at is equal to h plus rho z h minus p at z is equal to 0 upon h plus this is equal to 0. What we have done is we basically introduce this into this. What we have taken r common and LCM h, so that the whole term will come under this. And to make this look similar, that is p plus z is equal to h minus p at z is equal to 0, we have introduced rho g naught. So now the whole term, this p at z is equal to h plus rho g h at p at z is equal to 0 and rho z 0, it will look similar, so that we will reduce the whole term into a modified pressure term. This is given by r times this is modified pressure at z is equal to h and modified pressure at z is equal to 0. This is plus d time dr of r times tau rz. So this is our differential form of, that is our torque, differential form of our shear stress. Sorry, not torque, this is shear stress. This is minus times of this. So now to get our shear stress expression, we have to integrate it. And for integration, we can put the value of tau rz, that is Newton, from the Newton's law of viscosity, as minus mu r dvz upon dr is equal to minus of modified pressure, change in modified pressure into delta r. And we have two boundary condition, that at r is equal to 0, vz is equal to 0, that is no slip boundary condition, and at r is equal to kappa r, vz is equal to minus v naught, that is at r is equal to 0, we can see that the surface is moving with, this is our cylindrical system and this is the slag. So at r is equal to kappa r, that is at this location, it is the fluid is moving with the same velocity that is having this slag. So this is at r is equal to kappa r, we have the Vz is equal to minus times V naught because it is moving in downward direction and we have taken the Z direction positive upward. So that's why it is V naught. Now putting the value of this integration and doing the our integration, that is minus mu times R dou Vz upon dou R is equal to this R square plus C1. Now we will divide the whole expression by doing by mu times r, that is dvz upon dr is given by modified delta change in modified pressure upon 2 times mu h r plus c1 upon mu r. Now we again integrate to get our velocity expression, that is which is a function of r, which is given by delta change in modified pressure upon 4 times mu h into r square plus c1 upon mu ln r plus c2. And we have the two boundary condition which we use to get the value of this c1 and c2. So by applying the boundary condition, we get Vz at kappa r is equal to change in modified pressure upon 4 times mu h kappa r minus c upon mu ln kr kappa r plus c2 is equal to minus v times v naught. And we putting at r is equal to capital R, we have velocity 0, which is no slip boundary condition. So on solving, we get C1 is equal to mu upon ln 1 by k, change in modified pressure into r square upon 4 times mu h into 1 minus k square minus v naught, that is terminal velocity. And C2 is given by change in modified pressure r square upon 4 times mu h bracket open, that is 1 minus k square ln r upon ln 1 minus k minus 1 minus ln r upon ln 1 minus k into v naught. So this is what we get on rearranging this system. So now we will put, this is our expression, this is our final expression for velocity, and here we have the two constant of integration c1 and c2. We have find it out by using our boundary condition. So now putting the values of boundary condition in this expression, we will get the expression of our final velocity profile, which is a function of r, is given by modified pressure at z is equal to h and modified pressure at z is equal to r, which can be also called as change in modified pressure upon 4 times mu h r square minus ln r upon ln 1 minus k bracket open, change in modified pressure r square upon 4 times mu h into 1 minus k square minus v naught plus change in modified pressure r square upon 4 times mu h into 1 minus k square ln r by ln k minus 1 minus ln r by ln 1 minus k into v naught. So this is our final expression for velocity, which is a function of r. We also have to find the viscosity in terms of terminal velocity v naught. So for that, this is our system. To determine the viscosity, the sum of forces in z direction will be considered. So sum of forces in z direction. So there are total 5 forces acting on this system. That is first buoyancy force, force on the top layer, on the top of the surface, force at the bottom, and the gravitational force. And this is also the viscous force as playing in the role. So the gravitational force is given by density of slag, that is this, into volume of slag into acceleration. Density into volume, mass, and this is acceleration, that is the force. Buoyancy force is given by density of fluid, volume of slag into acceleration, and this is given by rho times pi kappa r square kappa r whole square h into z. Viscous force is equal to shearing stress into surface area, and shear stress is given by minus tau rz r at kappa r into 2 pi kappa r into h. And force at the bottom is given by pressure at the bottom into surface area. This is change in modified pressure at z is equal to 0 into pi of kappa r ka whole square. Force at the top is given by pressure at top into surface area. This is modified pressure at h, z is equal to h into its surface area pi times kappa r square. This is same. Just the change in pressure. Pressure at z is equal to h and z is equal to 0. The minus sign in the shearing stress, this is the minus sign. The minus sign in the shearing stress is due to the fact that the fluid is in the annulus is at the higher radius on the slag surface, which has the lower radius. So that's why we have used the minus sign in this. So by putting viscous force is given by minus times tau rz at r equal to kappa r into its cross-sectional area, that is 2 pi kappa r into h. By putting the value of tau rz, this is given by minus mu dou vz upon dou r. Vz is a function of r. The one term also comes, that is v r upon upon dz, where vr is equal to 0, though that term will be cancelled out. So that's why we directly use the expression minus mu times dou vz upon dou r into r is equal to kappa r times cross sectional area. So here on doing the calculations, that is dou vz upon dou r at r equal to kappa r is given by 2 pi kappa r h times mu. So now we will put the value of d upon dvz upon dr from the expression that we got earlier, that is this expression. We will differentiate it with respect to r and then we put it in this expression, which is given by minus v naught upon kappa r into 1 minus k square upon 1 minus k square minus of 1 minus k square ln 1 by k into 2 times 2 pi k kappa r 2 pi kappa r h into mu. So finally, the expression is given by minus 1 minus kappa r upon 1 minus kappa r square minus 1 minus kappa r ln 1 by k into 2 pi h mu times v naught. This is the relation between the viscosity and the terminal velocity.